Somewhere in the ocean, the surface is glowing, currents are shifting without warning, and entire coastlines are quietly being reshaped by forces you cannot see. Welcome to Relaxing Facts Studio, where we break down the hidden systems that control Earth in a calm, clear, and deeply fascinating way. In today's episode, we explore why tidal waves are becoming harder to predict, and how oceans respond to forces that span from the moon's gravity to the shape of the seafloor itself. What looks like random motion is actually a structured system still being decoded by science, one layer at a time. At night, sections of the ocean can suddenly glow as waves break along the surface. Tiny drifting organisms called dinoflagellates respond to water movement by producing brief flashes of blue light, even from something as small as a fish passing nearby. That light forms through a chemical reaction triggered by physical disturbance. Inside each cell, a molecule called luciferin reacts with oxygen, activated by the enzyme luciferase. The reaction releases energy as visible light instead of heat, while cellular ATP controls how strongly the glow appears across different conditions. Globally, these glowing events concentrate in nutrient-rich coastal waters where ocean upwelling supports dense plankton populations. Satellite imaging systems measure surface radiance and map bloom zones that can extend for hundreds of kilometers. Seasonal temperature shifts and currents influence how often and how intensely these luminous regions appear. In still water, most organisms remain invisible against the dark ocean background. When waves, predators, or currents disturb them, light output increases rapidly. Deeper ocean zones rarely show similar activity because limited nutrients and absence of sunlight reduce population density and biological energy availability. Researchers view this response as both a defense strategy and a communication signal within plankton communities. It helps confuse predators while also revealing ecosystem activity patterns. Modern optical sensors use these light signatures to monitor marine health, offering insight into food web stability and long-term coastal environmental change. In some parts of the ocean, currents suddenly bend, slow down, or split without warning as they pass over the seafloor. Underwater mountain ranges, deep trenches, and long submarine canyons redirect moving water, sometimes visible through drifting sediment clouds or shifts in surface texture detected by sonar mapping systems. This happens because water movement is constrained by underwater topography that reshapes pressure gradients and flow direction. As currents interact with varying depth, they adjust into geostrophic balance, where Coriolis force and pressure differences stabilize large-scale motion. Bathymetry, or seafloor shape, effectively acts as a guide rail for ocean circulation patterns. On a planetary level, mid-ocean ridges stretch for tens of thousands of kilometers, continuously shaping deep ocean circulation. Entire basins like the Atlantic and Pacific Channel water masses that travel at different depths, forming layered systems such as thermohaline circulation. These structures distribute heat and nutrients across the global ocean network. Where the seafloor is relatively flat, currents tend to move in broader, more predictable paths with gradual shifts. In contrast, rugged regions create localized acceleration zones, turbulence, and eddies that can persist for weeks. Even small variations in elevation, sometimes just hundreds of meters, can redirect massive water volumes. These hidden structures play a critical role in climate prediction models because they influence heat transport between equator and poles. They also affect submarine navigation routes, undersea cable placement, and acoustic detection systems. As mapping resolution improves, scientists continue refining how underwater landscapes shape long-term ocean stability. Along many coastlines, the ocean rises and falls in a slow, repeating rhythm that can flood beaches within hours and then pull back just as predictably. Boats that were floating earlier can end up resting on exposed seabed. This visible shift follows a timing pattern that repeats roughly every 12 hours in many regions. That movement happens because the ocean is being pulled unevenly across Earth's surface by a distant force. The Moon's gravity creates a tidal bulge on the side facing it and another on the opposite side. This differential pull is described through gravitational tidal forcing, where inertia and gravity interact across a rotating Earth system. Across the entire planet, this gravitational interaction produces synchronized tidal cycles that travel through connected ocean basins. The Earth-Moon system behaves like a coupled orbital structure, with angular momentum exchange influencing long-term rotation speed. Satellite altimetry missions measure sea surface height changes with centimeter precision to track these repeating global patterns. In smaller enclosed seas, tides often appear weaker or delayed because surrounding landmasses restrict water movement. In open oceans, tidal waves propagate freely and can span entire basins with consistent timing. Even two nearby coastlines can experience different tidal ranges due to resonance effects and local basin geometry. These predictable variations are essential for coastal navigation, energy planning, and ecosystem timing in intertidal zones. However, small changes in ocean mass distribution, such as melting ice or shifting currents, can slightly alter tidal timing and height. This is why modern prediction models continuously integrate gravitational physics with real-time satellite observations. Along many shorelines, massive walls and curved barriers stand directly in the path of incoming waves, breaking their force before they reach land. Some coastlines instead use sloped sand structures that absorb impact gradually, reducing erosion after storms that can reshape beaches within a single tidal cycle. These structures are designed around how water transfers momentum into solid surfaces. When waves hit, energy is distributed through pressure, turbulence, and friction. Engineers model this using hydrodynamic load calculations, where wave height, period, and density determine force on coastal materials and foundation stability. On a larger scale, modern coastal systems extend across entire metropolitan regions, combining seawalls, breakwaters, and drainage networks that manage storm surge over tens of kilometers. Some floating infrastructure adapts to sea level changes using buoyant platforms, while computer simulations test extreme wave scenarios generated by cyclonic storm models. Rigid concrete barriers provide strong protection but reflect wave energy, which can increase erosion nearby. In contrast, Nature-based designs like mangrove buffers and reef restoration dissipate energy gradually, reducing peak impact. The difference becomes more pronounced during extreme weather when wave energy increases exponentially with wind speed. As sea levels continue to shift and storm intensity becomes less predictable, coastal engineering increasingly blends structural design with ecological systems. This hybrid approach improves long-term resilience while reducing maintenance costs. It also reflects a shift from resisting the ocean to working with its natural energy distribution patterns. Along certain coastlines, cliffs and exposed shorelines reveal stacked layers of sand, clay, and shell fragments, each marking a former shoreline position. These layers appear like a vertical timeline, where darker bands often signal storm events that rapidly deposited material during high-energy ocean conditions. This record forms through sediment deposition, where waves, rivers, and tides transport particles that gradually settle and compact over time. Under pressure, these sediments lithify into sedimentary rock, preserving microfossils and chemical signatures that reflect ocean temperature, salinity, and biological activity at the time of formation. Over millions of years, tectonic uplift can expose entire coastal sequences that once formed on ancient seabeds. Geological cores drilled from continental margins can extend hundreds of meters deep, allowing scientists to reconstruct sea level fluctuations across glacial and interglacial cycles recorded in isotopic ratios like oxygen-18 variation. In stable coastal zones, sediment builds up slowly and preserves fine, continuous records of environmental change. In contrast, high-energy coastlines frequently erase older layers through erosion, creating gaps in the geological timeline. Even nearby regions can show completely different preservation quality depending on wave exposure and sediment supply. These layered archives allow researchers to reconstruct past ocean temperatures, storm frequency, and shoreline shifts with surprising precision. They also help calibrate climate models by providing long-term baselines that extend far beyond direct human observation, revealing how ocean systems respond to gradual planetary-scale environmental change. Along many beaches, sand forms repeating ridges that shift after every incoming wave. These ripple-like structures appear within minutes as water moves back and forth across the shoreline. Even a light tide can reorganize the surface into precise, evenly spaced patterns that stretch parallel to the waterline for long distances. This happens because moving water applies frictional shear stress on loose sand grains. As waves oscillate, particles lift, roll, and settle in repeating cycles. Grain size distribution and fluid velocity determine spacing, a process described in sediment transport dynamics, where threshold flow conditions control when movement begins or stops. Across entire coastlines, these small patterns scale into large geomorphic systems shaped by wave energy budgets. Storm-driven waves can reshape kilometers of shoreline in a single event, redistributing millions of cubic meters of sediment. Satellite imaging and lidar mapping track how coastal profiles shift seasonally under changing wave climates. In sheltered bays, sand formations remain stable longer because wave energy is reduced and sediment movement is limited. In exposed ocean-facing beaches, patterns constantly reset as strong wave action repeatedly erases previous structures. The difference becomes most visible during seasonal storm cycles when energy input sharply increases. These repeating formations act as natural records of coastal energy conditions, preserving information about wave direction and intensity. Researchers use them to understand shoreline resilience and erosion risk. Over time, even small changes in wave frequency can alter beach geometry, affecting ecosystems and human coastal infrastructure stability. In coastal zones where tides rise and fall daily, organisms are repeatedly exposed to both water and air within short time windows. Crabs hide under rocks during low tide, while mussels tightly clamp onto surfaces to avoid drying out. This constant environmental switching creates a highly unstable living boundary. That instability drives biological adaptation through selective pressure on survival traits. Species that endure salinity swings and oxygen variation rely on osmoregulation, a physiological process that balances internal salt concentration. Cellular stress proteins activate during exposure changes, helping marine organisms maintain function across rapid environmental transitions. Across global shorelines, tidal zones span thousands of kilometers, forming one of Earth's most dynamic ecological systems. Genetic variation in coastal species reflects long-term exposure to localized wave energy, temperature shifts, and nutrient availability. Over generations, these pressures shape population-level evolution measurable through DNA sequencing comparisons. In deep ocean environments, conditions remain relatively stable, with minimal temperature fluctuation and constant pressure. Coastal species, however, experience extreme variability within hours. This difference leads to faster adaptive evolution near shorelines, where survival depends on flexibility rather than long-term environmental consistency. These adaptation patterns influence broader ecological resilience, especially as climate change increases coastal variability. Species that evolve in tidal zones often develop traits like rapid reproduction cycles and structural flexibility. These same mechanisms are now studied in biomimetic engineering, where natural adaptation strategies inspire durable coastal materials and responsive design systems. When people stand near the shoreline, their breathing often slows without conscious effort as waves roll in and out at a steady rhythm. The repetitive motion of water creates a predictable sensory pattern, where sound, movement, and distance remain consistent for long periods without sudden change. This response is linked to how the brain processes rhythmic auditory input. Low-frequency wave sounds stimulate neural entrainment, where electrical activity in the brain subtly aligns with external patterns. The autonomic nervous system shifts toward parasympathetic dominance, reducing heart rate variability through vagal nerve activation. Across coastal populations, studies using wearable biometric sensors show measurable reductions in cortisol levels during extended exposure to ocean environments. The effect is amplified in regions with consistent surf conditions, where acoustic frequencies between roughly 0.1 and 0.5 Hz mirror resting physiological cycles such as respiration and heartbeat regulation. In urban environments, Sudden noise spikes and irregular visual inputs keep sensory processing in a state of constant adjustment. By contrast, ocean settings provide low-complexity stimuli that reduce cognitive load. Even visually, the horizon line offers a stable reference point that minimizes spatial uncertainty in perception. These environmental conditions influence how humans recover from mental fatigue and stress accumulation. While not a medical intervention, coastal exposure is widely studied in environmental psychology for its restorative effects. It also informs design principles in architecture, where soundscapes and visual continuity are used to replicate similar calming patterns indoors. Across satellite maps, ocean currents form vast, shifting ribbons of moving water that circle continents and cross entire basins. Warm water flows poleward in some regions, while colder water sinks and returns at depth, creating a constant three-dimensional circulation that never fully stops. This movement is driven by density differences in seawater, controlled by temperature and salinity. Warmer water expands and rises, while colder, saltier water becomes denser and sinks. This process, known as thermohaline circulation, links surface currents with deep ocean flows into a single interconnected transport system. On a planetary scale, this circulation moves heat energy equivalent to thousands of power plants, redistributing solar energy from equatorial regions toward higher latitudes. The Atlantic meridional overturning circulation alone spans thousands of kilometers and connects surface waters with deep return currents that can take centuries to complete a full cycle. In the upper ocean, currents respond quickly to wind patterns and seasonal atmospheric changes. At depth, movement is far slower and more stable, governed mainly by long-term density gradients rather than short-term weather systems. This creates a layered ocean structure where fast and slow circulation coexist. These interconnected flows act as a stabilizing system for Earth's climate by regulating heat storage and distribution. Even small disruptions in circulation strength can influence regional weather patterns over time. Because of this, ocean monitoring systems continuously track temperature, salinity, and current velocity to detect early shifts in global balance. What we've just seen is not separate stories, but one connected system shaping every shoreline, current, and coastline pattern on Earth. From microscopic light in the ocean to planetary scale circulation, each process is part of a continuous balance that is still being measured, still being understood. Thank you for watching Relaxing Facts Studio and spending this time with me. If you haven't already, subscribe so you don't miss what comes next. Like the video to help it reach more people, and share it on your social media so others can discover it too. Most importantly, leave a comment with your thoughts, what stood out to you, and how this changed the way you see the ocean. Your support genuinely keeps this channel alive and allows it to continue producing episodes like this.